Hi there. Welcome to lecture 15 of Fox. We are going to be talking about probability. So this is the beginning of our module on probability. Now, look who has shown up for this lecture. Orange Malik. So that tells you something. Probability is important. Okay, now, we're computer scientists. We are writing programs to solve problems in the real world. Okay, and we have to accept that in the real world, things are random. Packets sent across the internet, some of them get dropped. When you try to access the Wi-Fi, sometimes you succeed, sometimes you fail, and multiple people might try, and the number of people who might try at any given instant is kind of random. Okay, so this word random is thrown around a lot. Okay, and so, that's because things that happen in the real world are, in some sense, random, whatever that means. Okay. And if we want to know how our algorithms behave in the real world, we need to deal with this randomness. We need to analyze our algorithms in the context of this randomness that exists in the real world, whatever randomness means. Okay. So probability is absolutely essential for knowing how algorithms will work in the real world. But we've come around full circle now, and today we find that certain problems are very hard to solve until you inject a little bit of randomness into the algorithm. So it's not enough that the world itself is random. Sometimes we have to inject randomness into the algorithm in order to make it behave well, even for non-random inputs. Oh, so let that sink in. What? Yes. So many of the algorithms that, make real-world applications go have randomness built in. So the output of the algorithm, it can be random, or the running time of the algorithm can be random. And without the randomness that's injected into those algorithms just don't go. And so, not only is probability relevant for knowing how your deterministic algorithms will behave in the real world, probability is relevant because it makes algorithms that wouldn't otherwise work very efficiently work pretty efficiently by injecting randomness into the algorithm. And then to analyze such randomized algorithms, we need the tools of probability. So probability has just become a very important tool in computer science. And, that's why we have Orange Malik. Okay. Now, what does random, or what does probable mean? Well, Aristotle said it. The probable is what usually happens. Is that okay? So we are not going to focus on the philosophy, the axiomatic development of probability. So we're going to treat probability as this important tool, and there's a sort of a mechanics, a certain arithmetic in probability. So there's a mechanics to computing probabilities. So this mechanics, this arithmetic, gives us a prescription for computing certain numbers that represent the outcomes when randomness is present. And so we're just going to use that arithmetic, we're just going to use that mechanics to compute these probabilities and see how we can use them to understand, things that are going on in the real world. We're not going to, we're going to leave the philosophizing and etc. and axiomatic development to the mathematicians. Okay? We are going to focus on the mechanics of probability. And, in the realm of, probability, you can illustrate all the ideas and all the essential tools using what's called discrete probability. And this is a course in discrete math, so it's only appropriate that we focus on discrete probability. So that means probabilities where we're dealing with discrete objects. Okay. All right. Now, before we start going on probability, a related topic is actually counting. So let's just review what we did last lecture. So last lecture, we talked about counting. We talked about counting sequences with and without repetition, subset with and without repetition, anagram sequences with a specified number of, each type of object. Okay, and the essential idea is when you count, complex objects, you can think of constructing a sequence of instructions to construct the object and then count the number of ways of implementing those instructions. Okay. Then we introduced a sort of an advanced technique called the principle of inclusion-exclusion. Essentially, it's a way to extend the sum rule. So the sum rule is the fundamental rule. You can even derive the product rule from the sum rule. So the sum rule is the fundamental rule, but the sum rule applied to disjoint sets. So we discussed how to, extend the sum rule to the case where the sets are not disjoint, and that became the principle of inclusion and exclusion. So that's a pretty powerful technique, but it's a little bit more of an advanced technique. So you'll need a little more practice with inclusion and exclusion if you want to get good at it. So do the exercises in the previous chapter. also talked about the pigeonhole principle. That's not an advanced technique. That is a very simple principle, but it's a very important principle, and it can lead to stunning conclusions if you can figure out how to, creatively decide what are your pigeons and how to creatively decide what are your pigeonholes. And if there are more pigeons than pigeonholes, then, there are at least 2 or more pigeons in a pigeonhole. And then that's an existence argument. So it shows that there exist 2 or more pigeons in the pigeonhole. And, that shows that something exists, 2 or more pigeons. And if those 2 pigeons match in some property, then you've just proved that there exists 2 or more things that match in that property. Okay, whatever it is, whether it was social twins or matching subsets, and we did some examples last time. Okay. Now, today, probability. Probability is related to counting. You can think of counting as sort of, the hard size of a set. And you can think of probability as some kind of a soft size of the set. Anyway, but let's not philosophize too much. We're going to focus on the mechanics of probability, so we'll spend a lot of time today talking about how to compute probabilities and do a bunch of examples. Okay. And then discuss a little bit of the sort of mathematical foundations of probability. The mathematical foundations of probability lie within the mathematical foundations of sets. So we'll talk about probability and sets. And then we'll discuss, certain situations where computing probabilities can be much easier than the general case. And these are sort of uniform probability spaces where things are uniformly distributed. At the end, I'll touch on the concept of infinite probability spaces. So in the context of discrete probability spaces. Okay. And so let's begin. You've probably heard on the radio or the weather channel that the chance of rain tomorrow is 40%. And have you ever stopped to think, what exactly does that mean? Because tomorrow it's either going to rain or it's not going to rain. So what's this business of 40%? Okay, so let's sort of try to interpret this statement a little, and that's the extent to which we're going to philosophize about probability. Now, there's the sort of subjective degree of belief approach, which says my degree of belief, my level of certainty for rain tomorrow is 40%. Okay, that's a little bit too soft for my liking, and it's very vague, and I don't really know what that actually means, subjective degree of belief. Okay, there's another sort of quantitative view which says, this 40% is related to the quantity of rain. Imagine it could rain 0 up to 100 milliliters of, up to 100 millimeters of rain tomorrow. So 40% roughly sounds like we'll get about 40 millimeters. That's what I'm saying. That's also not quite accurate. So what what it's sort of intending to convey, okay, is sort of a more practical, more objective view of the world. Where imagine, okay, if we repeated tomorrow 100 times. Did I say more practical view? Well, let's just play along a little, okay, because we're just trying to interpret this statement. Imagine if you could repeat tomorrow 100 times, then on 40 of those days it's gonna rain. That's what that sentence is saying. That's the frequentist view. And that's the view we're going to take, the sort of operational, the practical, the objective view. Now, of course, it's not easy for us to repeat tomorrow 100 times. So we have to take that view with a grain of salt, or we have to consider experiments that are repeatable, where this argument sort of makes sense. Okay? And so let's consider coins. So someone gives you a fair coin. What does that mean? We could say that the chances are 50% that the fair coin will flip heads. And now we can repeat the following experiment. Flip the coin. Okay, so flip it 100 times. And what this sentence says is that on 50 of those, flips, or roughly speaking, 50 of those flips, you're going to get a heads. Okay? So this is this frequentist view, and that's the view that we're going to be taking. That's the view that's sort of appropriate to the computational side, the mechanical side of probability, which is what we're going to be focusing on. How do we compute probabilities, and what good are they? What can we use them to do? Okay? And probability is used in all kinds of fields today: economics, physics, computer science, biology, statistics, and so on and so forth. It's all over the place. Okay? So, let's think about some other experiments, okay, having to do with fair coins, and I'll just pose these questions, and then we will see where they lead us. Okay. So, the first question: you toss a fair coin 3 times. Okay. How many heads will you get? Well, that's related to this 50%. But now let's think about this. You toss a fair coin 3 times, and this 50% says I should get 1.5 heads. Okay, so that's a little weird. So you toss a fair coin 3 times, how many heads will you get? Okay, think about that question. Here's another question for you to think about. You toss a coin, and you keep tossing a coin until you get a head. Okay, so it's related. It's related to coins. Okay, and We like coins because we can do things with coins repeatedly, like flip them. Okay, you toss a coin and you keep flipping until you get a heads. How many tosses will you make? Okay, so think about this. Let's just think about what are the answers to these two questions. So if we try to literally interpret the 50% because they're fair coins, the coin that's flipped 3 times, we are expecting to get 1.5, heads. No, that's not possible. Okay, not possible. Okay, you'll get either 0, 1, 2, or 3 heads when you flip it 3 times. Okay, and how many times do you have to will you make a coin flip until you get a head? Okay, so the fundamental thing that you should take away from these two relatively simple everyday questions is there's no answer. Okay, and that's the idea behind probability. That's the idea behind randomness. There's no answer. The outcome is uncertain. And you won't know the outcome until you actually do the experiment. So until you actually toss the coin 3 times, you won't know how many heads you will get. Okay? And until you toss the coin, and until you run experiment 2 where you toss a coin until you get a head, you won't know how many tosses you make. Okay? Now, but nevertheless, we would like to sort of think about and analyze these 2 experiments before we actually go and do them. For example, do I want to do the experiments? I need a way to analyze these experiments, and probability handles such settings. Okay? It's this beautiful mathematics that can handle such settings where you don't know the outcome is uncertain. Okay, now for some history. Let me tell you a little bit about the birth of mathematical probability, and it's an interesting story. Okay, so there's an interesting character, Antoine Gombeau, Chevalier de Mer, and he's a gambler, and in his wheeling and dealing, he wants to know, should I bet even money on at least 1 double 6 in 24 rolls of a pair of dice? Okay, so you roll the pair of dice 24 times, and if a double 6 appears, you win. Okay, is it worth even money? He also had the question, what about at least 1 6 in 4 rolls of a die? Okay, so you roll the die 4 times, if a 6 appears, you win. Is that worth even money? Now, he's just a gambler, he's no mathematician, so he calls upon the great Blaise Pascal. Now Pascal, remember Pascal's triangle? So the great Blaise Pascal, and asks, what should I do? Should I bet even money on these gambles? Pascal thinks, this is an interesting question. Let's bring in the other great giant, this big, huge giant, Pierre de Fermat. And you may have heard of Fermat's last theorem. Okay, Fermat was a great mathematician. So Fermat gets into this conversation, and there's this correspondence that's been ignited between Pascal and Fermat, and this correspondence is what ignited the birth of mathematical probability. And today, it's this very formal, mathematical, very rigorous discipline that can be used to analyze the real world, randomness in the real world, randomness in algorithms. But it all started with a question about a very simple gamble. See if you can answer this question. Meanwhile, we are going to start simpler and work our way through computing probabilities. So let's move to the board.